Okay, let's get started. You're doing your homework, right? Okay, check the deadline, and you're working on your presentation, right? Make sure you are prepared. Third, we talked about it, but just reinstate. So for presentation, since I won't be around the week final exam, most likely, and so we mentioned the Friday, the week before. So everybody works for that. Just to 100% make sure that we. Interesting. So I have a seminar for you. I'll send it email. Okay, so
Thank you.
sorry, I do have a family. This is the week after. Well, I will be in Switzerland for 2 weeks. I will be gone. Okay, so sorry. Yes, I was gonna suggest June 7th. I just realized that I have to go to give a talk. What time is it? Anyway, so I'll check my schedule. Sorry for that, and I send an email. And then you guys can provide your own news. Okay. What else? Any questions? Any concerns? Any complaints? Not that big deal. So let's start. So last time we started discussion of renormalization, and I realized that probably I said something too quick. So let me clarify that point, and then we move on. All right. So we started a discussion of renormalization again. So for this, we start with the easiest possible theory, which is scalar field theory, real scalar in this case. Okay, and then we added a single interaction term, identical theory. So so you're asking, suppose I'm an experimentalist. So I'm going to measure, first of all, 2 phi come in, 2 phi come out. So I ask, obviously, experimentalists wouldn't care. I mean, they do. They don't need to know exactly what you're talking about. So long as it is a theorist's job, like what kind of theory can possibly explain this phenomenon that is observed at the experiment. So if this is the truth of the nature, then this plot can come from perturbatively. So if I call this to be IN, the amplitude. So this will get a distribution from crossover in lambda and so on and so forth. So there is a perturbation theory expansion. And then the first diagram will be just discrete level diagram. And then the second one will be set of diagrams, as we talked about, like so. And then you can keep going, so high orders and so on and so forth. So then this will be just minus I times lambda according to the final rules. And then we start talking about this thing. And then I said, for just to simplify discussion, I'm gonna just focus on this, because we can in principle cook up the theory that this is only relevant diagram. And then the question, yes.
So what the explicit definition of the amplitude M?
The explicit definition of amplitude M. So if you have a S matrix, this can be decomposed as identity plus transition amplitude. And then transition amplitude can further be written as 2 pi to the 4th momentum conserving delta function M. So IM is T, so IT, stripping of this momentum conserving delta function. Okay? So I2, sorry, IM2. So if I just come to this diagram, we wrote down there's 2 vertices, minus I lambda square. There's a geometric vector because you can play, we get the same answers. There's the 1/2. And then we write down the momentum integral, so that it looks like E for K, where here K is the momentum integral. And then since I'm talking about scalar field theory with the mass, did I say I'm going to study massless theory? I can do either way. So for now, let's set mass to 0. Then one of the momentum is just the K, so propagated is 1/k squared. And the other, given total momentum going in like so,
The second one is p minus k squared. So the first observation we made was that this this amplitude, in the limit where k squared goes to infinity in the Euclidean sense. I will make precise what I mean by this Euclidean sense in a minute, because we will talk about rotating to a Euclidean signature rather than Lorentzian. Okay, for now, you just read this as whatever. If this goes to infinity, then naively the amplitude goes up like d4 to the k over k to the 4, which is logarithmically divergent. Let me just write this way. So we know if we naively compute this, we're not going to get a sensible answer for now. 2. So that's the thing that I was trying to explain last time. But let's do it concretely. So given an amplitude as a function of external momentum, okay, or I used to write as s, which is p squared, okay, square of the total momentum. Then in this particular example, if I do a derivative with respect to s, if you want to put I, so what, let's see. So this is -1, that is -1, minus I. Anyway, so this, let me put I. So then this as a function of s is what? Like dp mu. I'm doing the chain rule. dp mu that I am s. So this, to be totally pedantic, inverse. And then this is a square of p. It's p2 times p mu. So that is the inverse of that. So I'm gonna have this. But instead I can write it as a 2s p mu by multiplying and dividing by p. Okay, so that's that factor. What about this factor? Let's just work it out. So that factor is going to be, so let's start to compute this. So that is lambda square over 2. And then, well, I'm not sure if I actually want to compute this because, okay, let me just write down the answer, overall answer. Why? Because in order to actually compute this correctly, which I can write down the answer according to this expression, I have to do analytic continuation anyway. So instead of going through calculation, which we will develop, if you do this calculation, which you will learn once again, you get the following answer. So for now, the purpose of this discussion is not to convey you compute this and you have a problem, but I just want to convey, concept of renormalization first before we jump into the calculation, as I alluded to last time. Good. So if you do this calculation, you get minus 32 pi squared lambda squared whole over s. So the claim is this looks divergent. But if I take the derivative, you can get a finite answer. So the key point here is this is finite. In particular, this is not sensitive to anything about super high momentum mode here. This is the exact answer. So let's continue. Then this. Now do the computation. We get minus, I think there's a factor of I mistake. Anyway, log of s plus integration constant. Next, I just literally integrate back. So now let's try to understand what this constant could be. We said that, even before computing anything, I know that this is UV divergent in the sense that the divergence comes from weak K mode, right? And then not only that we know this is UV divergent, we actually know the form of UV divergence. In this case, it is a logarithmically divergent. So this should be divergent. This is finite. I know C should contain divergence in it. And not only it should contain divergence in it, it must contain logarithmic divergence in it. But also, since it's dimension full parameter, it doesn't make sense to write log of s itself, right? Because if you Taylor expand, basically you will have a power series as everything has different unit. That doesn't make any sense in physics. Okay, so therefore, the good choice of a C in such a way that it would look like s over some cutoff scale
lambda. So let me explain what I mean by that expression. What do I mean again? So I'm about to compute this thing. And then actually, I'm gonna actually literally do the computation of, instead of calling S, let me call S prime as integration variable. And then we said, okay, the derivative integrand is S prime. Now, I'm gonna do the computation, this integration with hard cutoff in the momentum. So if you do it, you get log of S prime, and then you have to put, suppose I integrate from the IR value S, you might say, why am I doing the opposite way? You will see why. And up to some definite maximal momentum that I can think of, lambda squared. And if you do it, you get this. So now you might ask, oh, okay, naively you have to do like S to the lambda squared. Why did I flip that? Because that way, if I take the derivative with respect to S, I get this with the correct sign. So I just know which one I have to put. So this is an example of computing things with a hard momentum cutoff. So conceptually, what I have done is the following. I know that the trouble comes from the region of the momentum where it is a very, very large. Okay, so super short distance region. Now we have to either fully understand what is exactly physics happening at such a high energy scale, or if you believe in the fact that I'm interested in processes at pretty low energy, like only energy of the order of P, okay, like GeV machine. I don't care Planckian energy physics. So if you believe in the notion of the decoupling of the UV physics from the IR physics, meaning what that means is that if I'm interested in understanding physics that's super low energy, deep UV physics should not control what's happening here. Okay, there should be a notion of decoupling of UV versus IR. UV means high energy, IR means the low energy. So under the assumption that there's a decoupling between UV and IR physics, then whatever I see in the IR should be insensitive to what actually happens in the UV. What that means is that I must have a right to design what might be in the UV physics. And then I might be designing different ways. It shouldn't care. Because if I do change, something happens in the UV, once again, according to the assumption of decoupling between UV and IR, nothing must affect in the infrared. So we will get into that in a slightly more systematic way. But anyway, sort of modeling or parameterizing or deforming what really happens at deep IR, sorry, deep UV, high energy physics, to render apparently divergent integral into the finite expression is called the regularization. We will get to that soon. But again, in this case, I had in mind of modeling, or again, deforming deep UV in terms of sharp cutoff. So this is called hard momentum cutoff. Okay, so I'm just gonna say, I'm gonna integrate. Around some point, nothing should happen above that. This is how I say model my deep UV aspect of it. And in fact, if you do that, this is the expression you get. You might say, oh, have I conquered the divergence problem? No. All I have done so far, so see here, is if you want, all I have done so far is a parameterization of UV divergence. And in fact, if you take lambda squared goes to infinity, as if I should include all the momentum mode all the way up to the infinity, you recover logarithmic divergence again. So this is literally just a parameterization of the divergence, not the curing or turning actual divergence into a finite value. So far, I only have done parameterization, and such a parameterization, once again, is called regularization. I'm regulating infinity into a finite looking expression, but secretly, even explicitly, it's not actually finite. You just encode it in terms of notation instead of putting infinity. Good. Okay, so far, so that's what I talked about last night. And then I wanted to say something much more general about this sort of prescription. Okay, so what I meant was the following. Let me just try, and if it gets too complicated, we can just ignore that. So the last time what I said was this. Suppose I have a general one loop diagram. Okay, so I can have some fermion, some scalar. I can imagine all kind of complicated one loop diagram like so. Okay, so for instance, there's kind of incoming momentum P1, P2, and so on and so forth, all the way up to Pn. And suppose I have a loop momentum K. So then, this will become P1 plus K, P1 plus P2K, and so on and so forth. Okay? So then generically, this one loop amplitude will take the following form. First of all, there's going to be integration over single loop momentum. Okay? Meaning, I'm going to integrate from the very big loop to the very small loop. So I'm just summing over all possible sizes. All right? Then, okay, there's a whole list of propagators. So there's a K-square propagator. Let me drop the mass term for now. And then like P1 plus K square propagator. And if you want, you can put all these IH prescriptions. And then eventually P1 plus P2 whatever. P minus 1 plus K propagator. And so on and so forth. Okay, so there's a horrendous number of propagators. And then depending on the nature of interaction, numerator is a generally polynomial function of all external momenta, which let me just put as a set of PIs, and then all possible couplings, coupling constants. So this is the generic structure of a one loop amplitude, without even specifying what the theory is. So assuming local perturbative quantum field theory, the most general one loop diagram will take this form of amplitude.
I don't understand. So if we any create one loop diagram, then can I just specify all the moments of the internal lines just by a single parameter K?
Yes. Yes. By definition, because there's a single loop going in. The only difference is because of the vertex, you just have to match the momentum conservation. That's why explicit value changes. But one loop means one loop integration. Okay. Now, this may be horrendously divergent. I don't know. It can blow up like many different ways. So this, depending on all nature of this details of this function, this can blow up like lambda to the n. If lambda I call hard momentum cutoff once again, like that I mentioned, right? Now, so for instance, lambda to the first appear in nature. Okay, so such a divergence is an example of what's known as cosmological constant. Okay, so this is dimension for energy density of a, if you wish, background universe. Lambda square appears, it's called quadratic divergence, or the radic divergence. And this appears for scalar field. So this famously appears for amplitude for a square. Keep going, there can be linear divergence. You can have lambda to 0, which secretly means that it's log of lambda. It's logarithmic divergence, as we encountered already. But the point is that, just like what we talked about here, if somebody had crazy UV divergent amplitude of that sort, then I can always take enough number of the derivatives so once again, let me just take that thing to be just IM. So then the point is that you should be able to take enough number of N1, P1N, N2, P2N2, and so on and so forth, and capital N, Pn, capital N, acting on this horrendous function. This may take all the external momentum data, such that it is eventually a finite, UV finite, okay, or UV insensitive. By UV insensitive, I mean if you take lambda goes to infinity, this thing stays to be finite. So you have many options. So you should definitely be able to render
divergent amplitude in this form, and then you can integrate back. So if I call this to be m tilde, which is finite, then you should be able to integrate back by integrating back m tilde. By doing so, you can get the structure. For instance, take an example. Suppose I had an example where there's a p square of some amplitude was finite. Let's take the example. Previously, we saw the example where by taking a single derivative was already finite. But let's just take an example where you have to take it twice. Then, what do you get? So first, integrating once. If you integrate this once, what do you get? First of all, you get m tilde once, and then you get one integration constant, like so. And then, if you do it twice, because you have to do it twice, then you get double integral, and then now this will get a momenta naively plus v. Okay, so in any moment, last time what I was trying to say was that in this way, A, you should always get the finite version of that thing by taking derivative. B, that was not ultimate goal. From that, you can sort of understand formal structure of original amplitude that you were interested in to study. This is how this will look like. Then what I said was the following. In general, this m tilde, in general, so this is, there's a good part, which is UV finite. UV finite. But there is a feature, which is not necessarily a bad thing. This is in general non-analytic function. Function of external momentum. Example, there's a law, for instance. P squared over times, as we saw, for instance. Okay, so this is non-analytic because it's not single value function as I explained last time. Okay, however, therefore, this part, like I said, therefore, this is UV finite, but in general, it's non-analytic function. What about this part? So there are two integration constants, and then this P is external momentum. And I know that this whole thing is UV sensitive or UV divergent, which means that this part should capture one. This should be UV divergent. And then this coefficient captures different kind of divergence according to this sort of classification. But these are, polynomial in external momentum. What it means is that if you go to the Cauchy space, they are local function in position. So all UV divergences always appear as a local in space and time, which makes sense because UV means a short distance. From our perspective, they look like a very, very small distance physics. Effectively, if you zoom out, they look like local. The UV divergences appears to be local. This is one of the key proof renormalizability of quantum fields.
Is it possible to have real hard momentum cutoff that is finite in real world, or it is not allowed to have in?
Okay, so your question is there any physical system where hard cutoff is actually realized in nature as the hard UV regulator?
I mean, in our universe, or any field theory, is it possible to have it?
So strictly, if you're asking whether hard cutoff ever realized, either in universe or condensed matter system or anything like that, I can't think of a concrete example. But we know certain regulator, not necessarily hard cutoff type, certain regulator actually will realize in nature. And best example is lattice regularization. In other words, it looks like a continuum, but if you zoom in, at some point, it is lattice of atoms or nuclei and stuff like that. Then they regulate automatically this structure. Okay. And for instance, string theory will provide a specific UV cutoff scale.
The point I wanna ask was that the integral rate about n tilde can have a range of various range, I think. And I think it is allowed to have finite reason of some range.
So you're asking whether this is a definite or indefinite integral? Is that your question, basically?
I think not. I think is it possible to define definite integral? I don't know.
Okay, so
Yeah.
so yeah, we start out with the indefinite integral in the sense that you just integrate over all the way to the infinite. So definite, but with the infinite range. That's correct. What that range saying, right? So, but when I took a derivative with respect to external momenta, but this is integral with respect to loop momenta. Okay, and I'm taking the derivative with respect to external momenta, which obviously does not have any range of integration.
Yes.
So I'm doing the indefinite integral path together. Okay. But you can tell me later if you still have a question about that, right? Okay, let's come back to this example because now I want to explain physics behind this. So what we have shown is that if I compute a one loop corrections to 2-to-2 scattering, I get this contribution, and then now we want to talk about physics behind this. So to raise this, then let's go back to this discussion.
그래서 하드 컷오프에서 하드가 무슨 말이에요?
Hard means I'm not gonna let you anyway. There's no negotiation. Get out. Anything above the lambda. As opposed to so. Okay, I mean, let me lead you in a little bit. No, like I'm just chopping up like this. That's what it means. Hard. Yes. Okay. Good. Good. So going back to the physics. So once again, we were taking, attitude of experimentalist. I'm just gonna measure it, and then this can include now minus. If I call this IM, this is I lambda. That was leading order contribution to that, and then I lambda square 32 pi square log S over capital lambda. This is regulated computation. Okay, I have not done the renormalization. Now we are going to talk about renormalization. So we're going to talk about this in two different ways. So number one. For the number one. So it's called either physical or point shell correlation. I will give you two different ways of tackling or understanding the question of renormalization. And the first version is this. So, and then eventually, hopefully, I will explain the distinction and relationship between those two features. So the first, here one observation, key point is this. So while the amplitude, so here, good. So the key observation number one, let me just write. Number one, lambda, which is Lagrangian parameter. One of the Lagrangian parameter is not unobservable. What do I mean by this? Well, when we write down the theory, we that Lagrangian parameter. So here is the form that we wrote down, and then we tried so far. We tried to make this as physical as possible, like say, oh, if you have 2-pi meeting, and then you see there's a probability of this process happen, which is proportional to this. So this says we try to interpret whenever we see interaction term in the Lagrangian. We try to give as much physical meaning to that as possible so far. So therefore, naturally, in your head, you have impression that this controls the rate of this process. This is not totally incorrect, but subtly so that this itself is not unobservable. So let me now explain what I mean by this. Really, observable is this. right? Meaning you shoot out the two particle, you measure the probability of having another particle comes out of that, you measure the probability. And or momentum dependence, everything you measure. And then this include all possible terms. And here I have completed only up to one loop order. In principle, in nature, if you measure, it includes ultimate, whatever, any orders in perturbation in principle. So when I say that, so point number 2, therefore observable is this, as I said just now. And then we need to know, so based on these two observations, now let me mention this. Even though, while this amplitude compute appears to be UV sensitive or UV divergent, but if you go about and measure this, guess what? You should get a finite answer, because this is an observable. So observable, therefore, should be finite. So probably let me state finite. But you might say, how does these two make sense? This definitely looks like UV divergent. And you tell me that this must be finite. What am I talking about here? Right? So the secret is that, therefore, to reconcile these two statements, and I come back in 5 seconds. Any thoughts?
Professor?
Yes.
Now we're trying to say that the S matrix is the only observable in our theory.
Not necessarily S matrix, because there are other physical observable, like instantaneous effect and stuff, which are not captured by an S matrix. But in this particular context, I'm only trying to make a distinction that Lagrangian parameters are not on its own observable. But in the context of S matrix, yes, I'm taking it as an example. It should be whatever this blob that is unobservable. So we should learn how to distinguish Lagrangian parameter versus actual observable. Okay, and it is that moment we can actually define what we mean by renormalization. Okay. Good. So the key point is this. So this has let me just say, a apparent UV divergence. Apparent meaning you can see by eye already. There's a log lambda squared. But in order for this to be a finite, lambda parameter in this first picture, crucially, in this first picture, lambda itself has actually UV sensitivity. So the parameter actually have UV sensitivity. You can say, what kind of UV sensitivity does this has? It depends on your calculation. Meaning, if you compute up to this point, as I show you now, you can determine what kind of UV sensitivity lambda must have in such a way that this, as an observable, can be finite. Yes.
The sensitivity of the UV sensitivity of the lambda is an assumption, or just kind of hand-wavy explanation.
So it's neither an assumption nor a hand-waving explanation. This is based on the fact that I'm computing this observable using theory, right? And then if I compute it, it looks like we got this apparent UV divergence. That's observation number 2. But I know as a physicist that this should give me a finite answer if I measure it.
It is kind of induction.
Yes, if you want. So therefore, lambda, the Bayer parameter, usually called the Bayer parameter or Lagrangian parameter. UV sensitivity such that observables, example, that thing is finite. So now I'm going to actually show through the calculation what I mean by this. So good. So suppose let me define a in terms of this. Suppose let me define a lambda r, which I observe. So this is going to be called renormalized eventually. Renormalize the coupling. I will define. Well, really, at this point, what I mean by that is that this is just if I go out and measure a particular energy scale as 0. So in other words, I'll actually do this experiment at a particular energy scale as 0. And then I call whatever the outcome of the measurement to be my lambda r. Okay, I know this should be finite if I go and measure it. And so there's a fancy name called the renormalized decoupling, but this at the end of the day is observed value. So therefore finite. This at a scale, fixed scale as 0. So that scale, when I actually define this particular quantity, is called renormalization scale. Okay, so then according to this expression, what that means is that lambda minus lambda square 30 pi square log of S0, a particular scale, lambda square. So this is my definition, and I know this must be finite, and then I'm about to determine what sort of UV sensitivity this parameter has to have so that this is actually finite. So let's see. So since we are dealing with perturbation theory, in this context, when I say we are doing perturbation theory, what I mean is that if you measure this, if you go and actually measure, this is not that small. I'm sorry, this is not that big. Okay, so there is a sense which, okay, there is a small interaction. That's what I mean. What it means is that this is small, right? The actual measurement turned out to be small. That's what I mean by perturbation theory. So therefore, I should be able to rewrite the parameter in terms of the perturbation series, like A, lambda, R, and so on and so forth. And then you can keep going. I'm sorry, I'm just doing the perturbation theory because this is a small, just expanding. And then I'm about to determine A, the parameter A, in such a way that if I plug in B, I determine the UV sensitivity of lambda, so that this expression should come out automatically to be defined. Let's see. So let's plug in. Lambda r is equal to, first I'm writing to second order in lambda r, the observed value. So approximately, up to that order, I'm just gonna keep the first frame. Square, 32 pi square, log x0 lambda square plus da da da. But since I'm only working at second order in perturbation theory, let me just keep the first order here. And then I demand that that is finite. Not only it's finite, but according to this particular equality, observed value lambda r. So, some minus sign has messed up your minus sign, so it should be all plus here. That should be all plus here. So the equality is satisfied to see if A is actually minus of 1 over 32 squared as 0 lambda, right? Just testing that. So what it means is that Lagrangian parameter or Baire parameter, like I argued or showed, I said, it must have a UV sensitivity. And here we actually understand that the specific form of UV sensitivity. Okay. So this is finite, this is not finite. And now this apparent sensitivity is only UV sensitivity. And so this actually tells you exactly how this parameter should be sensitive to the UV scale.
That's something with what's the Baire parameter lambda.
Baire parameter, I just gave you another name, but if you want, you can just call it a Lagrangian parameter.
It also depends on the causal scale large lambda.
Yes. So good. So then Okay, what is concept here? You really need to get a concept here. I take this here, I compute things, I see an explicit divergence, but I believe that whatever I do, this should be matched on finite observable. And one way to think about that is that this parameter has to behave, has to play in such a way that if you give me that sensitivity, I swing against that so that I cancel, I will only give you finite answer. If you compute higher order corrections, you might get different form of UV sensitivity. And this guy say, haha, okay, let me play a little bit differently, such that again I can cancel all this UV sensitivity, give you finite answer.
I have one more question about the. So the lambda equals to UV sensitivity, which means that when the cutoff scale lambda goes to infinity,
Yeah.
the error parameter goes to infinity.
But so what must be so good? So yeah, what must be finite is an observable. This is a tool for you to perform intermediate calculation. Okay, obviously, if you take the infinity at this level already, you might say, okay, everything is divergent, I don't know what to do. Remember, I have only regulated the computation so that instead of me seeing infinity, I just see how it is UV sensitive. This is a parameterization of UV divergence. Like so here. So at the order of a lambda square in perturbation theory, to one loop order, this will plays out such that it picks up the exactly correct UV sensitivity, so that eventually you only get the final observable quantity that you wish. So if you take the lambda to infinity at the end of the calculation, then everything works out and you only get the final answer. Okay, good. So now, but let me continue. So let me keep this. Second version, some of you may have seen it, and you might say, okay, Lagrange parameter is not finite, you add the counter term, blah, blah, which I will present now too. But this perspective must have at least conceptually in your mind. So now what I have done is, so far, we had one parameter, and then we made one measurement. This. So since I had a one parameter in the theory, and then I made a one observation, using that I have a fixed what this lambda has to be. Right? So in this way, I related a parameter to an observation. Okay? You can consider general cases. Suppose you have a field theory with n parameters, and you want to make n independent observations, by which you fix that n parameters in terms of observables. Okay? Then, crucially, so that's not the end. Crucially, then, after this, so after this, once that set has done, now we start making predictions of the theory. Okay, so far this is the fitting, right? Since I have n parameter, if you give me n data point, I can fit those n parameters. Every theory can do that, right? If you give me theory to 5 parameter, I can give you 5 observables, fit it. So at this level, we cannot distinguish which theory is correct theory of the nature. After the fitting, now we start making prediction. So that means that there's self-consistencies. And using this, we can now test which theory is the correct one. Suppose after this, now let me ask the question of, okay, now I'm going to actually, look at the same measurement at different energy scale as which is different from S0 that I use to fix. Okay, so then what happens? Let's do that. So that thing is minus lambda according to that expression. But now I know what this is in terms of an observable at scale S0. Right? So let's write the thing. So that if I do it, what do I get? Minus lambda r minus lambda r squared, 32 squared, S0 lambda squared. So that's the first term I'm writing. Second term,
I'm just gonna write up to second order. So in this case, I just need to plug in only the leading order here. Lambda r squared, vertify square, log s over lambda squared. So if you do it, what you get is, for this new process at different energy, what you should get is that's not. So now this is absolutely finite answer. So one measurement, remember this is nothing but measurement at different scale as not, right? So this provide you sharp relationship between two different observables whose relationship are absolutely finite. There is no UV divergence. Okay, so I could have said the other way around. Yes, here there is a apparent divergence, but if you actually look at the difference between the two observables at different scales, that relation will come out to be finite. So I use one observation to fix the parameter, and then after that I start making, oh, if I do measure at different scale, what should I expect to get? Now I can, as a theorist, I can tell you, well, you should expect that that quantity is not a random value. It should be exactly this. If that is the prediction, this is how we can start making a test on of the proposed theories. Okay? Yes.
So my question is that in this formula, I think the lambda,
Which
small lambda, is also dependent on the F naught.
Yes, because I fixed the parameter according to a certain fixed observable, which is measured at S naught. It's called Reynolds scale. For instance, electric charge. You might say, what is electric charge? Well, I heard 1/137, but that is measured as specific energy scale. Electric charge changes if you change the scale of the measurement. It's called RG running. He will tell us. All right. So almost every observables in nature are scale dependent, unless we talk about conformal field theory. Some of you are taking, then there's no scale changes. But most of the physics, including the thing that I'm talking about here, depends on the scale of the operation. Okay, electric charge. You might say, oh, is that just one? No, everything changes. Okay, gauge coupling changes, electromagnetism coupling changes, gravity changes, everything changes, and therefore these concepts are by basically almost every quantum field theory based theory or phenomena.
So the S naught is the scale of the theory or experiment.
Yes, this is a measurement made at that energy scale. And then I call that to whatever my observable. And in terms of that, this parameter will be fixed according to that particular observable, which depends on the scale of measurement.
And the large lambda is just it doesn't have any physical meaning or not.
At this point, once again, we know that if an IV calculation have a UV sensitivity, but this is how I parameterize the UV sensitivity. So probably you might want to wait a little bit, because later I'm going to compute another computation, not using hard momentum cutoff. I'm going to compute different way. You will see that UV sensitivity may come out in a different form. But who cares? At the end of the day, what we are interested in is relationship among IR observables. That is the prediction made by theory.
So our proposal is that the unit of the dependence of the UV sensitive parameter large lambda.
So I say it again.
So our proposal is that the observable should be not dependent on the UV sensitivity.
Absolutely, absolutely. Any infrared physics observable should be independent of the UV physics parameterization. It's called regularization independence. We will get there more systematically. Okay, good. All right, so just keep in mind, renormalization, there is a sharp finite relationship among observables. Okay, if you hand me theory with 5 parameters, I have to go out at least measure five observables, and then I can fix those parameters in terms of observables. After that, I can compute million different observables,
there should be sharp prediction based on here. Okay, so that is how this thing works. Okay. Yes.
저기서 페널티 보도까지 보면서 나
Yes.
근데 저기 큐빅이나 펄티 보도까지 무조건 봐야 되는 그래서 그런 거는 이제 띄어에 따라서 알겠습니다.
Good. So the question was, what is the justification of a computing, say, up to 3 level, up to 1 level, up to another higher level? Who determines that? So that is determined based on precision of your machine. Suppose your machine can determine maybe it's 1 or 2, which means that your precision is 100%. You can make 100% error. Or suppose somebody else has a better machine who can give you 1% precise data. Then, in order to test our theory, if I only compute 3 level, which I'm making 100% error bar, I cannot tell which one is correct here. So if I have 5 different theories to test, at that point, theoretical calculation has to perform such that theoretical uncertainty also matches experimental uncertainty. So therefore, these days, experimental precision goes up really high, exquisitely precise, which means that there's a high demand on the theory side, that we have to also compute a lot of loops, because we want to make precise theoretical predictions among different theories. Then we can test. Is that clear? So therefore, I specify precision of the question. Okay, I'm going to measure this physics, but I need this to be 0.0001% precise. That will tell me at what loop order I should compute. Okay, and then everything is conceptually the same. Just much more harder calculation. That's very important question. And this concept is precisely why, hopefully we'll get there. What is so-called non-renormalized field theory are super predictive. All days people thought that non-renormalized theory are garbage, and we should take care of them at all. Because of that, meaning ultimate answer is the precision and then calculation. And even for non-renormalized field theory, once you specify precision, then there is a final order calculation one has to do. So in that case, we can also talk about predictivity of the non-renormalized field theories. We will hopefully get there. Okay. Good. So now I want to talk about the second viewpoint. And I'm sure there will be confusions and chaos, because I just told you, and you might thought, I think I got it. And I'm just gonna tell you a second story, and there's a myth of God, right? So be alert. So it's the second viewpoint. What did I use? This? Anyway. Second version is called renormalized perturbation. Previous one was on-shell renormalized perturbation theory. This is called renormalized perturbation. Key is you need to know which version people are talking about. Okay, so here the starting point is that now we take the parameter, Lagrange parameter, parameters are finite. Okay, so previously we said, okay, this guy somehow plays out and it changes its own UV sensitivity according to the calculation. But here, so this is just number, of course. Okay, this is usually how it is taught in QFT. So let's again take the same theory. And then since this is a finite, I'm going to use this notation. Okay, but you'll see how things work. This is finite. Whenever you see lambda sub r, I mean finite quantity. Okay, so now, and then you went on and compute now, right? So you went on and compute. And then you got, okay, good, tree level finite, beautiful, I know what I'm doing. And then you compute the second order, so the loop order. And then you found this, right? Now you're surprised. Shoot, this is now infinite, and I know this is finite, so I'm really talking about UV divergence, right? So this is now UV apparent UV divergence, which is in this language the only UV divergence. Therefore, now what do we do with this? So in this case, we do the following. Let me throw out a very confusing statement. No questions allowed. So quantum field theory is defined onto local counterterms. I said that.
Local counter tree.
Yes. So what do I mean by that? So here are original operators I wrote down. I'm going to write down a local counterterm. So I will at least explain the beginning of the word. So A, this is a local operator. Okay. And B, so there's a, therefore, this has the same form as the existing operators in the theory. I did not write down another random operator that does not look the same as before, right? With the terms that exist already. I wrote down a local operator who has the same form as the existing operators. And then I just throw out some parameters, which I call delta sub lambda. The purpose of this term is that it remedies this UV divergence. So how does that work? So now if I compute this theory with this modified theory, including local counterterm, local counterterm means what it does counteraction to do something good for you. So then what did you get? In this case, I will get, in addition to this, I should get delta lambda. And I design my counterterm such that I get find an answer order by order in Porter-Vacuum theory. In other words, at the first loop level, this is the only problem. And then I design my local counterterm in the same form as the term that existed in this theory. In general, you might have to do slightly more general thing, such that you get the final answer. Okay, so what do you need, therefore? So here I have to talk about possible choices for delta. Need more space, therefore. So, what are the choices of delta? This counterterm I should do? Well, the goal is to have a finite answer, right? But that alone does not uniquely fix the form of delta. So for instance, let me choose one possibility. Choice number one. Let me choose delta lambda to be so if I have chosen that, then if I compute this again, including counterterm contribution, I will get some fixed scale as 0. I get S as 0. So that's finite. So yes, I have designed properly the counterterm with the correct divergences so that I get the final answer. But just to illustrate my point, let me just move on and just write down the second possibility. In fact, there will be infinitely many different possibilities. And what would that be? Well, second time, let me choose a form of the counterterm which has this term, therefore it successfully, removes the UV divergence. And then let me throw out some random finite number, like 2.5. It's also giving the final answer, right? In fact, I can consider any other finite terms. So here, one point that I'm trying to deliver is that just getting the final answer does not uniquely fix counterterms. In fact, the relationship between the different counter terms are related by some finite pieces. Okay, infinite pieces sort of fixed to remedy that problem, but there's ambiguity by these finite pieces. In fact, what fixes this finite piece? So let me just write, therefore. The counter term. Now your fantasy, so I can just write CT for counter term is called either it's called renormalization scheme or it's called renormalization condition. So I will demonstrate now. So suppose I pick as a renormalization condition. I decide to use my renormalization condition or scheme to be as before. If I do measurement at a particular scale S, I want to get exactly lambda. So I demand, okay, you may design your own counter term, but you do so that if I do the measurement of that process at particular scale, this should give me exactly just minus lambda r, not rest of the terms. Okay, so I pick this as my condition. So let's see this uniquely fixes counter term. So here, if you do it, so this is equal to minus lambda r squared, 35 squared, 32 pi squared. I do measurement here, and then delta r should give me exactly lambda r. So that was my renormalization condition. Okay, and note that renormalization condition is made in terms of observables. It should be. Okay, that's the physical thing. And then if you do that, now there's no ambiguity. It must be exactly this, nothing else. And another important point that to make. So basically then, with the counter term, now your Lagrangian can be written as so the relationship between this renormalized perturbation theory approaches to the renormalization and then own shell approaches to the renormalization I talked about previously. The relationship is that previously we called this to be my Baire parameter. And then whose UV sensitivity is automatically fixed once I specify which observable I called it a renormalized coupling. Here, instead, we started out with finite valued parameter, and it's as if I actively design and add extra counter terms so that I render everything finite. So it's either you take a passive or God-given perspective. I'm not gonna do anything. Let me just call this, which automatically has a correct UV sensitivity. So long as I define what I call to be normalized coupling, this parameter will pick up to automatically correct UV sensitivity, and then it plays out so that I always get the final observable answer. And then you get the final relationship between among the observables. Okay? And in this second picture, I start out with this, which is easy start because I'm talking about a number. Okay? And then I compute, I have a problem. Now, this path, I have to take an active designer point of view. Now I'm gonna actively add the counter terms to conquer these divergences, and then I get the final answer. And then you need, actively design this term. Once again, precise form of the term is fixed by this condition. Normalization scheme. That's what that means. Yes.
So in the last line of the left part, I mean the upper one, yeah, n equal to blah blah. And so we ignore the second order term of delta lambda.
Second order term of the lambda.
Delta lambda.
Sure, here, you mean?
Yeah.
Yes.
And that is because we assumed it is small. right? Delta lambda is small.
Oh, so your question is why I don't include a like loop diagram with a delta? Is that your
Yeah,
question? Good. So that's because it's order by order. So we are doing perturbation theory. But starting with the tree, I add one loop, I have a problem. And then I want to have a counter, which is not a loop, but a tree level local operator, which is powerful enough to keep the problem from the one loop. Next time, okay, I'm in the happy position where this theory is one loop finite. That's how I designed this, right? Then suppose I complete this two loop calculation, which now include two loops made of original bare parameter, one loop including counter terms, and then mixed terms, all of that. It will have extra divergences that I did not have before. Then I have this old UV divergences. But remember, all UV divergences are local. I show you. There is this polynomial momentum dollar UV divergence are all local, which means that all this problem, which now involves not only higher loops of this, lower loops of that, mixed loops, should be cancelled by having another counter term, which is yet more powerful to kill this divergences. Keep going like that. Okay, so extra loop with a divergence, extra local counter term to kill it. And then I go to the next step, I will have a loop now involving counter terms as well. And those new divergences will be removed again by higher order counter terms.
Thank you. Can you repeat the first sentence you said? So contemplate theories and then
I can repeat that, but I'm not going to explain.
okay.
Quantum field theories are defined up to local counter terms.
Okay. I just wanted to.
Yeah. All right. So this is good. I hope you get this concept. This is important. Let's move on. Now we're gonna talk about serious calculation because at this point everything was just a conceptual, not calculation. But getting this concept is like 50% of your knowledge, maybe more than 50%. If you lose here, the rest of the calculation is like what the heck. Okay, if you get this, you don't lose the way. You know why you're computing this. So this is to me one of the most important things about knowledge, getting the concept. Okay, so with that intro, now we want to talk about renormalization of QED step by step. Okay, and so the first thing we want to talk about, so as a part of the renormalization, QED, so there are a couple of things we have to look at. The first thing is what's called vacuum polarization. Then there's a vertex correction. Then there's electron cell energy. Yes.
But big question about that. Who is the first carried out the calculation to you?
I think there was a lamp shift calculation that involved probably RG, sorry, not RG, loop diagrams. Tomonaga, okay, probably I should look it up, the correct names. Just curious who actually first faced these divergences. Good question. Both I suffered first. But historically, at least, not that I actually read original historical stories, at least from the book, I saw the author saying people almost gave up on QED. Like, okay, we can't play with this point. This is too nasty talk. Throw that out. And then eventually people figured out like how to think about divergences and things like that. So, okay, so we're gonna go through this, and then hopefully eventually we can confirm the word Takashi identity that I derived. We will get that again back once we have all this calculation done in time. So first of all, today we will do a vacuum polarization. Vacuum polarization can be thought of as if you have a charge here in space and time here. Then photon propagate, and then tree level, you just talk about this, right? So the charge there's another charge, there's an electromagnetic interaction, which can be thought of as exchange of photons. Now, that's tree level. Then, obviously, at one loop level, you know that we can talk about this. Right? So, since I have a current coupled to photon, we can talk about this. And then you can keep going. You can add higher loops. Principle, higher loops, like this, many other diagrams. But obviously, we're going to just focus on the one loop first. Okay, now actually computing things. The reason why this is called a vacuum polarization is simply because if you had a piece of stuff, I don't know, like dielectric material. And then if you apply the external electric field, obviously it will be polarized. Right? So it's polarized. So then here what happens is that this is a vacuum. Okay, nothing's there, no material. But then if you apply electric field, temporarily there's E minus E plus. So vacuum is sort of polarized for a very short period of time, and then it comes back. But this happens all the time. So therefore vacuum knows that there's electric field applied to the vacuum, and then it knows how to depolarize, borrowing energy from the vacuum. Okay, so that's why it's called the vacuum polarization. Vertex, we're going to study. Well, so this is a tree level vertex. Okay, there's electron, positron coupled to photon. And then we're going to talk about extra corrections, like something like this. This is a one loop diagram, so we have to look at that. Electron center energy. This is like corrections to the photon propagator. And then you should ask the same question. What about the correction to the electron propagator, fermion propagator? So again, here tree level looks like this, right? And then there will be corrections, for instance, this. And there are many higher order diagrams, but again, we're going to focus on that, this. So that's the goal. Okay. So here I'm following discussion by Matt Schwartz and the both. So we're gonna tackle not writing down these loop diagrams already in terms of fermions and vectors, which has vector indices, fermion spinors, and so on and so forth. We can do that, but then you have to deal with both, gamma matrices, traces, and polarization stuff, and then on top of that, divergences. So instead of that approach, we're going to get rid of all unnecessary complication for now. We're going to replace everything with scalars as a first path. So we first start with the Python to study a diagram that looks like this. So for this, we take real scalar field theory, and then we have a bunch of cube instead of like the first that we talked about.
So can you explain why we choose probably by qubits?
Good. So we can literally do it for QED, like fermion vector boson. Okay, then what we want to learn as the first path is how to think about UV divergences, how to compute things like that. So I don't want to deal with all the spinors and vector polarizations, extra structures that can impose extra technicalities on top of UV divergences that we want to conquer. So let's get rid of all those unnecessary features, spinor, vector. So we just replace everything to scalar. So we first study only pure real scalar, and then only look at the diagram that looks exactly like this, understand the divergence. Okay, 10 minutes, because we're going to have a seminar here at 4. So let's look at the process diagram. So here, my amplitude now is at tree level, it's propagator, scalar propagator. And then at one loop level, it will be this.
So that looks identical to that, so we want to compute this. So again, let me call this to be M2, and this is M1. We know M1, so let's just compute M2. There's a two couplings, that's IG squared, divided by, there is again symmetry factor if you go back and recall yourself, 1/2. And then that's the sign. So if I call this to be P, good. So this is P, and you do the same. So here I call K the blue momenta. Then if I look at this arrow, that should be that plus that is this. That means that is that minus that. Good. MFC. Good. So there's a one integral over 4 momenta.
Am I talking about massless? Massive. Okay, massive. Fine.
K squared minus M squared. That's 1. And then P minus K squared minus M squared. And then obviously in principle there's I epsilon. Let me put that in. I want to explain of significance of that.
So let's first understand what's known as the superficial degree of divergence. So let's first check how divergent this is. Which is easy to check because now if you again naive Euclidean sense of taking K squared goes to infinite limit, this has 4 powers of K in the numerator, and then there's another 4 powers in the denominator. Okay, so you should expect that this should be log divergent. Good. Now, instead of just doing this, we are going to actually compute this. So there are a couple of technical steps. This is the beginning of that not so boring discussion of techniques to learn. Okay, so how to compute things. So as a first thing, as part of that tool set, the first thing we want to know is what's known as a Feynman parameter. Feynman parameterization or Feynman parametry, whatever you call it. So this, there are a couple of identities. So if you have an integrand, product of the two, like 1/8 times B structure. So this is literally that, right? So this integrand is 1/8 times 1/B. This is like 1/8 times B. And this is the same as integration from 0 to 1 over some auxiliary parameter x called the Feynman parameter. And then this is equal to x times a 100 x times b squared. So it's the same exact. Or another way of writing the same thing, which will be useful when we generalize this to many factors, is x plus a plus y times b squared, and then delta x plus y. I mean, if you just perform y integral using delta, this will get back to there. Now the question is why this is true. Well, that's true because it is. So, so to show you that, I'm not sure I need to show. You can do integration, yes? No. No. So a minus b x plus b squared, right? So what do you do? Well, just call this to be u parameter z, right? Then first of all, since you define that way, you have that 1/a minus b, then b is that square. Then the limit is when this is 0, that's b. When this is 1, that's a. You know how to do this. Okay, you should. Okay, so there are a couple of more formulas of that kind. The second thing, like a times b, same factor to the n power.
We have this new final parameters. Once again, x plus y minus 1, x plus y minus 1. Yeah, I said it correctly. Good. Very good. Okay. Y times a, y times b to the n plus 1. N times y and then. Okay, so that's a little bit more complicated looking. But basically, what you have to do is you take the derivative with respect to b on 1 over a times b is equal to 12. You keep generating higher powers in the b. Okay, eventually you should get this. Third, let's talk about slightly more general expression. A1, A2, suppose you have n factors, like so. And if you recall, the most general one-loop amplitude I wrote down has this form, right? There's a lot of propagators, so you have each propagators, some numerators. So we should have this form. In this case, you have n final parameters, which is the same number I have as the factors in the denominator. And then you have this delta function again. And the first thing that this is add up to 1. And then you have x1, a1, xn again to the n. And n minus 1. So this, in case you're curious, you can prove it by induction. So first you can start with n equal 2, which we proved. And then you want to prove if the nth version is true, you want to show what about we have an n plus 1 factor, and then you try to run the proof by induction. In the mirror step, you may need something like this one, where you can prove this. Okay. Now, with the 4 minutes left, probably I have to stop here. But next time we're going to actually compute this. There are a couple more. Let me just tell you what will come soon. Next time, we will, in order to evaluate this integral, we will have to go from Minkowskian signature where zeroth component versus special component has a different sign in metric. Okay? So we will go to a Euclidean signature where everybody has a plus sign. Okay, but that sort of analytic continuation from the Minkowski to what? Euclidean would not be possible naively. I will discuss. Would not be possible naively. And Feynman tree brings a beautiful light on that aspect. So it's not just one of the computational tricks. Without this, at least apparently, that rotation that you want to do would not look possible. I'll explain. And then I will explain that in the Euclidean version of that integral, how we can actually do the computation. We will develop the general techniques. And then we go back to physics to discuss the meaning of it. All right, so that's all for today. We will continue on Thursday.